Let's analyze our charging capacitor again, where we have an ideal battery, we have a resistor, and we have our capacitor in a circuit. We have a switch. We close S at t equals 0. And what we want to do is look at the current as a function of time, the charge on the capacitor as a function of time, the voltage across the capacitor as a function of time. The first thing we want to do is get the differential equation that defines this circuit. So again, we pick our conventions. We have a current, a circulation direction, a plus Q, and a minus Q. Now, we write out our circuit equation, which is the EMF as we cross the battery, minus IR, minus Q over C is 0. And because we're charging the capacitor, we have minus dq dt, R minus Q over C is 0. Now, just in terms of words, this is a first order. The function of this differential equation is Q. Q of t and its derivative are the quantities of interest. And they're both functions of time. Remember, that's what we're calling the current. Now, this is a first order linear differential equation. Why is it linear? Because Q is raised to the 1 power. And there's a constant term in this differential equation, so we call that a first order linear inhomogeneous differential equation. It's just terminology. What we want to understand is what is the behavior of Q as a function of time. Now, for these linear equations, there's something we can always do, which is we can separate the rate of change of dq dt. So let's write this equation as dq dt equals, so we bring this to the other side, that's E minus Q over C, we divide by R, and this is our starting place that we want to think about. So let's draw a plot of Q as a function of t and try to ask ourselves what happens without doing an analytic solution. Well, the first thing is we have to ask ourselves, what is the charge on the capacitor at t equals 0? So let's assume that the capacitor is uncharged. So at t equal to 0, what we see is there's no charge on the capacitor, and the current is just E over R. And that's exactly what would happen if there were no current. So at t equal to 0, we could redraw our circuit just like this. It's just, I'm going to put a little dot there where the capacitor was, resistor, battery. And what we have here is that the capacitor is acting like a short at t equals 0, which just means a resistance-less wire is connecting the two terminals of the capacitor. This is only at t equals 0, and you can see that the current is E over R. Current equals E over R when there's no charge. So when you just close the switch, the capacitor acts like a short. It has no effect on the circuit. But remember, we use this model for the capacitor as a battery. Even though there is no charge on the capacitor, the rate of change of dq dt is non-zero, and so we have a slope. And let's draw that slope like that at t equals 0. So there is the slope, dq dt equals 0. Now, what does that mean? That means that the charge is building up. So as we start to build up a charge on the capacitor, our, quote, battery is starting to charge up. That's going to reduce the current in the circuit by this amount. And so at some time interval a little bit later, the slope will be a little bit less by how much charge is on the capacitor. Effectively, you can think that the capacitor is acting like a battery pointing the other way. This battery is overwhelming the capacitor because there's not that much charge on it, so current still flows in this direction. Now, as Q increases at a later time, we see once again that the slope decreases. This process goes on until eventually you can see that when these two quantities are equal, then the charge isn't changing anymore. And that's what we call fully charged capacitor. So what we have here is it's reaching a limit here, and the value here is when these two quantities are equal, and that's when the capacitor is fully charged, so we can say that Q final is just C times the EMF of the battery. That's no surprise. The potential difference across the battery is the same as the potential difference across the capacitor. No current flows anymore, and we get at T very large, we could call it infinity, that at this point we can draw our circuit like this, and now the capacitor is an open circuit because now I at t equals infinity is 0. This is I at t equals to 0. So not only have we qualitatively described the current, the charge on the capacitor, but we've also looked at its behavior right when we close the circuit and after a very long time. And that's an important way to think about a differential equation by not just treating them as symbols, but asking physically, what do these quantities actually mean? Now let's look at an analytic solution to our charging capacitor. So let's just quickly establish our circuit. At t equals 0, we close S, and the charge at t equals 0 on the capacitor is 0. What do we mean by charge on the capacitor? Well, remember, we have these conventions. We have I. We're just calling this our positive plate. This is a negative plate. This is a circulation direction. And so our equation, as before, was E minus IR minus Q over C is 0. That's the voltage drop across the capacitor. The current is charging, so we have E minus dq dt. R minus Q over C is 0. And again, we want to separate out the derivative. And so we write the equation like this. And now there's a technique to solving these first order equations, which we've looked at in some other examples, which is something we call separation by part. Separation by parts. What I want to do is get all the Q's to one side and the DT's to the other side. Now, what a lot of people do is they're a little confused by this because there's two terms, and they just try to take one term to the other side, and that doesn't work. What you have to do is you have to take this whole function, dq over E over R minus Q over RC to this side, and put the dt over to that side. Now, I can integrate both sides, and you may recognize this as a natural log, but to make this integral easier, I'm just going to do one more step, which is to pull out minus 1 over RC, and then this side becomes E times C, and over here, the minus sign plus Q. Now, I can just check my dimensions. Q and C times E is charge. That's dt. And I'll bring this term over to the other side. And so I now have a function that's just a little bit easier to integrate, minus dt over RC. Now, in doing integrations, you have to remember that in physics, we have initial and final conditions. And so this is not an indefinite integral, but when I integrate both sides, what am I integrating from? Well, I'm going to integrate t at t equals 0. We've said that's 0. And here's the key thing. I'm going to look at a time t and look at the charge at time t. That technically means this is an integration variable. T prime goes from 0. T prime equals t. So I put limits on both sides of the integral. And this is a natural log. So this side is natural log of q of t minus ce. And when you look at the minus another log, but log of a minus log of b is log of a over log of b. Here, q is 0, so I just get minus ce. And over here, I just get minus t over RC. Now keep in mind our little identity that e to the log of x is x. So I exponentiate both sides, and I get q of t minus CE minus CE. That's an e, I switch the order, is e to the minus t over RC. And now I just have to do a little bit of algebra. I'm going to bring this to this side and bring that term over there. And I get my solution to this equation, which is q of t equals c times the electromotive force times 1 minus e to the minus t over RC. And that's our solution. And if you plotted this solution as a function of time, q of t dt, you can see that when t is 0, we get 1. There's a minus sign in there. When t is 0, we get 1 minus 1. That's 0. No charge on the capacitor initially. When t is infinity, e to the minus infinity is 0. We just get the final charge on the capacitor, CE. And what we're getting is a function that's growing like that, which we already qualitatively understood. Now, there's two more things that I want to put here, which is, remember, in our charging case, the current is dq over dt. And so if I differentiate this, well, differentiating constant is 0. Differentiating e to the minus t over RC brings a minus 1 over RC. The minus signs cancel. The c's cancel. And I get simply e over r, e to the minus t over RC. And you may have recalled that the initial current, when I close the switch, is e over r. So my current, as a function of time, is decaying like that. And our next video will analyze how to think about what we call the time constant associated with the current falls off in this charging RC circuit. When we looked at our charging RC circuit, resistor, capacitor, I'm going to put a plus Q, minus Q, capacitor, current in the circuit, we saw that our solution for the charge was final charge times 1 minus e to the minus t over RC. And when we saw the derivative of the charge, we got e over r, e to the minus t over RC. Remember, our initial conditions were the capacitor was uncharged, and at t equals 0, capacitor acts like a short, so the initial current I naught was e over r. You can replace the capacitor with a wire. It's just an EMF with a resistor, so we could write that as E naught minus t over RC for the current as a function of time. Now, if we plot that function of current in our circuit as a function of time, it starts at its initial value, and it drops off exponentially. Now, any exponential decay function has a characteristic time to it, which we can think of, we call a time constant. So if you have any exponential function e to the minus t with some amplitude, then our time constant is 1 over a. So we can write that as e to the minus t over tau. This is what's referred to as the time constant. And in our particular case, we see that tau is equal to RC, which has the dimensions of seconds in. Now, what does a time constant mean? Well, let's look at first at t equals 0. So if we look at our current I, one time constant later, t equals tau. So I'm going to write my current as I naught e to the minus t over tau. When I set t equal to tau, this is I naught e to the minus 1, and that's 0.37 times I naught. So what happens is that if you wait one time constant from the initial value for an exponentially decaying function, the current drops off by a value e to the minus 1. But this is something that's even much more general for an exponential function. Let's just pick any point t1. Then the current at t equals t1 is equal to I naught e to the minus t1 over tau. Keep in mind tau is RC. Now, let's go one time constant later. So let's go to the point t1 plus tau. And let's see what the value of the current is at that point. So I at t1 plus tau is I naught e to the minus t1 plus tau divided by tau. And I can write that as I naught e to the minus t1 over tau, e to the minus a plus b is equal to e to the minus a, e to the minus b. And the other term is minus tau over tau, so that's e to the minus 1. Now, what is this first term? Well, that's exactly the current at time t1 times e to the minus 1. And so if this value here is I of t1, then if you wait one time constant later, you have the value that you started with at t1 times e to the minus 1. And that's why, for an exponential function, this quantity is characteristic of exponential decay, and it tells us, it gives us a qualitative concept of how the current is falling off as we charge up this capacitor.